So exploring transfer functions in Matlab, the TF command and its friends. That's how we're going to start. Jamie, thank you for interpreting what TF means to me. I am totally like, I get the WTF. The TF, I wasn't there yet, so thank you. Now I'm there. So the TF command allows us to create LTI transfer function objects, which we'll usually just call TF objects, that are recognized by LSIM, step, and initial, among other nice functions that we've seen in Matlab for doing simulations of dynamic systems. We've, in the past, used state space models, SS models, but now we'll see how to do that with transfer function models as well. So consider this transfer function. Okay, so looking at it, right away we recognize that it's what order? Third order, yep. The highest polynomial power in the denominator. It's third order. And that means we have 3 poles. And in the numerator, we see that there's 1, 0. There's one value of s for which the transfer function is 0, and that is s equals -1. So this is like just looking at it, we see that. We don't know if it's stable or unstable. If it's higher than second order, so it could be that there are some underdamped poles in here. So could have some oscillation that happens, or we could have an overdamped pair. We don't quite know. So, but that's possible. So we can make a Matlab TF model as follows. We'll give it sys. We'll assign this object a sys. We call it the TF function, and the arguments are the numerator first. So it's the numerator coefficients in descending order. So 1s plus 1, and then in the denominator we need the coefficients as well. So 1s cubed plus 3s squared, 3, plus 7s plus 1. And if we evaluate that and don't put a semicolon at the end of the line, we get this nice response that lets us sort of check visually if we typed it in correctly. Yeah?
If there's like a 0 for like s squared, do you have to put like a 0 in, or is it like?
You have to put a 0 in, yeah. Yeah. Mm-hmm.
So, like, say the transfer function isn't like a fraction, can you just write it without the denominator?
So if you have no coefficients of, say, the denominator, you have to give it an empty set of brackets. So
So you can't just...
You would do TF of, and then say the numerator was 5s plus 1, and the denominator has nothing in it. It would be, well, actually, the denominator would have a coefficient of 1.
that makes sense.
Yeah. So this transfer function.
Okay.
Yeah. Great. There's another way to do this, creating a TF model that I showed you. I don't really have a strong preference. I kind of like this first way better. There's a second way, which is very popular on the internet. So I thought I would include it because if you guys are looking around on the internet, you'll probably see this. And it's a little weird at first. So what you do first is you define the variable s to be a transfer function object. And what you're saying is the s coefficient is 1, the constant coefficient is 0, and in the denominator you just have 1. So this is a transfer function that's just s. So it's 1s plus 0 divided by 1, which is just S. And then what's cool is that if you then take that S object and you just build this transfer function ratio, so S plus 1 divided by S cubed plus 3S squared plus 7S plus 1, you just do that, MATLAB will say, oh, okay, what they want to do is create a new object, and since they put all this transfer function stuff in there, they want it to be a transfer function object, and it will happily create that for you and say, oh, each S here is just a transfer function Laplace domain S. And it gives you the same thing. So I just wanted to show you that there's that way to do it too. Some people find this to be useful because they get to write out the S cubed and all that. So it's just a matter of preference. Okay, so algebraic operations on transfer functions. We've already seen that you can start doing stuff with it. You can say S plus 1 because S is actually a transfer function in this line, but we'll look at that explicitly here. Say we have two transfer functions, G and H. So H, we'll say, is the sys we've already defined above. We might want to concatenate them. Okay, and I'll explain why you would want to. The idea is that we might take the output of G, so system G, and use it as the input to H. So if the output of G becomes input of H, then the transfer function from the input of G to the output of H is just G times H. Okay, so the idea is that there's a system that's represented by transfer function G, takes an input, has an output, and we take that output of G and we feed it right into the system that has transfer function H. And then we take the output of H. So if you want to know the transfer function, you just multiply G and H together from the input to G to the output of H. And so I just decided to make a new G here. And there are two different ways we could write this, right? So I already defined S to be this transfer function object. So I could use this way, or could use this way, which is to say 1 over S plus 2. And I just pulled this transfer function out of the air. Okay, I just was like, we just need a G. So say we had a G, and this is what it is. So we can multiply G and H, which I said is just going to be sys from above, and it'll return a nice transfer function object to us. Yeah?
So just to be clear, we've already defined S above as the transfer function. That's why you didn't have to type it out in this part.
Exactly, yeah. I'm just using S from above.
Okay.
Yeah. Yeah. Note that we have seen that MATLAB handles addition and multiplication of scalars and TFs, as well as the products of transfer functions, and it will also handle division, although we didn't explicitly show that in this section. So it'll do that. So what it does is it manipulates it as if S was the Laplace variable S in a symbolic representation of the transfer function, and it'll just do it. You don't actually need the symbolic toolbox to do this, though. The control systems toolbox, which handles TF and SS and all those functions, provides those functions, is all you need. So you're kind of doing something symbolically, even though it's not explicitly so. So combine those transfer functions. So it multiplied G, which is a first order system transfer function, with the third order that we had before, and we got a fourth order back. Okay? That's how it works if you have a nth order system and you multiply it by an mth order system, you get an n times mth order system. Or no, wait, you get an n plus mth order system, I should say.
Right?
Yes.
Yeah,
Yeah, because 3 plus 1.
exactly. It's
because they add.
it's plus addition.
Yeah, because of the flowers.
Yeah.
Yeah.
Yeah. It's because you're multiplying, I mean, if you want to think of it in terms of the transfer function, you're multiplying a polynomial of order n by a polynomial of order m, and that gives you a polynomial of order n plus m. Okay, so that's great. Very good. State space models to transfer function models. So consider the state space model shown below with these A, B, C, and D matrices. Yeah. Pardon? Yeah, you could just do different cells in Matlab. That'd be fine. I use the same namespace for this whole thing. So yeah. So A, B, C, and D. So how many state variables do we have? Two. It's a 2 by 2 A matrix, so it's got to multiply the state vector x. So it's a 2 by 2 A matrix, second order system, 2 state variables. How many inputs do we have? B is a 2 by 1 vector. It has to multiply the input vector u, right? Left multiply u, so it has to have 1 input, right? 2 by 1, and 1 has to match up with the input. So 1 input, and then output here, we've got a C and a D matrix that have 3 rows in them, right? So 3 rows mean that there are 3 outputs. So 1 input, 2 states, 3 outputs. Okay? So we can create a state space model as usual with this SS command, but we're interested in the transfer function models associated with this. So we can do it symbolically. This is our nice transfer function matrix equals C times Si minus A inverse B plus D equation, which allows us to convert. And we can do that symbolically if we like. I defined a symbolic capital S variable, and I just said, okay, C matrix times the inverse of S times, I needed the identity matrix, the size of the A matrix, right? So that syntax will give me that. Minus A, so the inverse is taken then, times B plus D. So just plugged it right into the formula and evaluated it. And I got these transfer functions out. So there are 3 of them. That makes sense, right? You get a matrix of transfer functions, 1 transfer function for each pair of input and output. So we had 1 input and 3 outputs. So we have the transfer function from the input to output 1, input to output 2, and the input to output 3. That's what these 3 rows are. Now, if we had 2 inputs, we would have a 3 by 2 matrix here, which would be input 1 to output 1, input 2 to output 2, input 1 to output 2, etc. So if you're just looking for the transfer function symbolically, this is an easy way to do that. Whoops, it's a 3 by 1 matrix. It was 2 by 1 and then I changed it. Okay, so it gave us a symbolic matrix of transfer functions, and we can interpret them as being those outputs, or those transfer functions from the one input to each of the outputs. Okay, or, so that was the symbolic derivation. So I just did, I mean, you guys actually have done this calculation before, right? You've done this, and you have to do an inverse, and you have to do a bunch of matrix multiplications, right? And I know you guys love doing that. So I literally just showed you guys how to do something in Matlab. It's like 2 lines, okay? It's very easy. Even though I'm not in love with symbolics in Matlab, like this is a very easy thing to do in Matlab. So it's nice. Or we can convert, I'll say, the SS model to a TF model. So we can actually simply pass the SS model that we created above, which we did right away, right? From our A, B, C, and D matrices. We can convert that to a transfer function model by just passing the state space model to the transfer function, the TF function. And it gives us a list of transfer functions. Yeah?
Wait, can you back to yeah, that part. So I guess I got a little lost there. So right there, we're transferring, we're converting it into a transfer function?
Yeah. So this is the standard
And then,
method of doing that.
but below we're doing the same thing.
We're doing the same thing, but we're not going to use symbolics. We're going to do the same thing, but we're going to just use the TF function to take this.
Same process, but we're getting slightly different results.
We're getting, I mean, the result is
I mean, it's going to come out.
equivalent mathematically, but
we could, so if we
yeah.
did the inverse low-cost transform, they should come out the same?
Correct.
Okay.
Yeah.
Okay.
Yeah. Yeah. So this
I got
one,
confused when I saw them, they're separate. I was-
yeah. So this one's giving you a list of symbolic representations of the transfer function, and that might be what you want for a given situation. This one's going to give us TF models. So the symbolic one, you can't simply do like LSIM on it, for instance. LSIM needs either a TF model or a state space SS model. Needs something like that. So if you want to do a simulation of it, the second route is going to be what you want, because it's going to give us a TF model. The previous one didn't actually give us a TF model in Matlab. It just gave us a symbolic representation of the transfer function, which is great in some cases. Sometimes that's what we want. Sometimes we want that symbolic representation. We might do something with it. But if you want the TF representation that we introduced above, which has a lot of applications we'll look at in just a moment, then you're going to want to go with the second route to use the TF function from your state space model. So, yeah.
Or we can, no, right, sorry.
So this gives us a TF model that has 3 outputs. So from the input to output 1 to output 2 to output 3. This is exactly the same result that we got above. So 1 over s plus 2, 1 over s plus 2. Just a sec. And then the second one, if you find the common denominator, which is s plus 2 times s plus 3, then in the numerator you have 2s plus 5, and in the denominator you have s squared plus 5s plus 6, which is what we have here. And then the last one, again, common denominator is s plus 3 in this case. So you have s plus 3 plus 1 in the numerator, s plus 4 divided by s plus 3. And that's the third transfer function. So they're equivalent in terms of the mathematical object they represent, but MATLAB is looking at them as different objects because one of them's symbolic and the other one's a TF object.
Is it because they're separate, like separate functions, like if it needs to be in a singular fraction?
It's because
'Cause I noticed
this could be any symbolic expression right here. It just happens to represent our transfer function. But MATLAB doesn't know that. And you could go back and let's see if we can do this. I haven't tried this, but I bet you can. So sys tfs is this. I think we can do a subs in S. Let's see. Old, new. Great. The old variable is big S. The new variable is little s. I don't know if it's going to let us because little s is not defined as symbolic. It's defined as a transfer function. But let's see. It's not going to let us. Unfortunately. Because that would be nice. Let's see if it plays nicer if we just take one of the transfer functions out. It still doesn't let us. I'm sure there's a way to go from a symbolic expression to the transfer function model. But there's an easier way in this case, so I wouldn't go that route. But I think that's possible. You could turn this into one of these objects, but I think it's going to take some parsing of it. So might not be straightforward. This is the easiest way, is to, if you have a state space model, you just define it as such in MATLAB as an SS object, and then TF will just say, oh, you have a state space model. I'll just build a TF model just like that, but with transfer functions from each input to each output. And it effectively uses this operation, but then builds a transfer function model for you. So we've got that. Note that there is a function called SS2TF for a state space model to transfer function model. I was playing around with that in the earlier section, and it has serious bugs and should not be trusted. So don't use that function. I have no idea why it's so buggy, but it literally is terrible. So, yeah.
Where did we define success?
Right here.
Okay, I missed that.
Yeah. So we've done this before, right? We've created a state space model by using the SS command and just giving it A, B, C, and D. Yeah. So, great. So we have two different ways. One of them gives us a transfer function model representation, which is great. Okay. Now, let's look at poles, zeros, and stability. So transfer function models are great, and we can look at the poles of it, which are the most important, the zeros of it, which are also of interest, and then stability from the poles, right? So let's do that. There are nice functions, pole and zero. We can just hand our system object. I just used the original sys we defined. And if you evaluate it, you get the 3 poles. It was a third order system, right? So 3 poles. And one of the big takeaways, remember, of the preceding lectures was that the poles are equal to the eigenvalues, which are equal to the roots of the characteristic equation. So if you have a transfer function model, you have poles. If you have a state space model, you have eigenvalues. If you have an input-output differential equation model, you have roots of your characteristic equation. So you could convert among these, or you could build separately, different means, a state space model and a transfer function model. One way to check to see if they're congruent with each other is to check to see if the poles are equal. So the poles of the transfer function are equal to the eigenvalues of the A matrix. So, I mean, we could have, I didn't, but we could see, for fun, let's compare the poles to the eigenvalues of the A matrix. So if we do Eig of A, I think it just returns the poles. Oh wait, we didn't have the A matrix for cis, did we? So never mind. That was a different system, right? The A matrix formed cis TF. We could look at that though, if you guys want. So we could do look at pole of cis TF, and oh, cis TF's got multiple, doesn't it? Let's see, what does cis TF have? Okay, so what cis TF is giving us is -2 as the pole here, -2 and -3 as the pole here, and then -3 as the pole there. So that's what's being listed here. I think there's probably a better way of getting the return to parse that a little bit better, but in any case, that was just an aside for comparing the eigenvalues of the A matrix to the poles of the transfer function model. Would have probably come out nicer if I had said the second one. Yeah. So if you just looked at one transfer function and look at the poles. -3, -2, -3, -2, they're equal. So that's fun. That was just a little aside. But for the system at hand, cis, it has 3 poles and 1 0. The 3 poles include a complex conjugate pair and a real pole, and then there's 1 0. We knew there were going to be 3 poles because it was third order. We knew there was going to be 1 0 because the numerator had a first order polynomial. So those are the poles and 0. Stability can be evaluated from the poles. The system is stable because the real parts of all poles are negative, right? So real part, negative, real part, negative, real part, negative. So we're stable. That's good news. It's great news, especially considering I made this transfer function up off the top of my head. So, okay, so it's stable. We also know from the lecture that it's interesting to look at the pole 0 map, okay, which is to look at where the poles are and the zeros are in the complex plane. So the PZ map function will give us a look at that. I know that these are a little small, but what we see is an X here, which corresponds to the pole at -0.15. So here, you see the -0.15 real pole shows up there. The complex conjugate pair then also shows up, so the -1.42 plus and minus 2.13 I also show up. And then wherever there's a 0, it puts an O. So X is for poles, O for zeros, and the 0 shows up at -1, which is real. So if you just wanted to look at the pole 0 map, that would also be a way to look at the stability of the system. The poles all show up in the left half plane, right? The left half plane of the complex plane. So they all have negative real parts, and therefore the system is stable. So that's another way to look at it. Okay, so now that we've got these TF models, let's go ahead and simulate. So all the simulation functions we've used for SS models, which include LSIM, step, impulse, and initial, will also work for TF models. Let's try a step response. So I define a time array. I'm going to go from 0 to 15 seconds, and I'll take 100 step or 100 time points in that array. This is something to think about. Okay, how do we know how long we should simulate stuff for? The location of the pole from here, the real part, tells us it tells us something about the decay rates, right? The ones that are more leftward have larger negative real parts, more negative real parts, and therefore the decay rates are faster. Okay, so these poles out here you can say are faster than this pole. And in fact, this pole is significantly slower because you look at the distance from 0. At 0, that pole would just it would just oscillate, right? If the real part was 0, it would oscillate or just not move. It wouldn't decay at all. So as you get closer and closer to it, you're going closer and closer to not decaying. You're decaying much more slowly. So these ones are actually almost 10 times further out than this one. So this one's going to dominate. This pole is going to dominate. And it's going to dominate at a time constant of, so the pole is at negative 0.152. So the time constant is the reciprocal of that. So 1 over 0.512 is about 2 seconds. So the time constant is 2 seconds. In 10 seconds then, five time constants, we should be 90-something% of the way there. So simulating for about 10 seconds, I chose 15, just to show a little bit more, is reasonable. If you have no idea how long to go, it makes sense to go back to your time constants and look at those decay rates. You can do some guess and check too, but you can miss stuff if you're not careful. We might not capture a lot of the faster decay rates because they're going to happen 10 times quicker essentially than the dominant one. But let's take a look. So we'll use step. We'll give it the transfer function model sys that we defined. We'll give it the time array that we defined. And then we'll plot it. So open up a new figure environment. Plot t comma y. The x label is time and the y label is the step response. And we get this, which our decay rate looks about right. The dominant decay rate then is the 2-second time constant. And we went like 7 time constants out here, so we're getting there to a final value. Notice this wiggle that happened early. So we don't have good resolution here because we only did 100 steps. But notice that there's this bump, sort of inflection that happens. And that is happening from those faster but underdamped poles. So these two poles over here are contributing that. So that wiggle happens because of those. If we did a little bit higher resolution, like 200, we could see that better, but it's really it's kind of subtle, right? It looks like, oh, it's just a decay, but that early stuff that happens is captured in the response and important to consider. If these things were not quite so fast, they would be causing some significant oscillation here. But instead, it just creates this little wiggle. Okay. All right. Any questions on transfer functions, especially in Matlab? Okay. Yeah. Oh, I just chose. I wanted to simulate the response to something, so
Okay.
I chose step because it's a nice one to interpret. And remember, one of the ways that we like to characterize the transient response of a system is in terms of the step response.
Right.
Might be interesting, just for fun, to do the impulse response, which is the response to a unit impulse input, so the direct delta function. That one's super fun, right? We see this initial jump in the value, and then it decays, and as it decays, it's also kind of oscillating, isn't it? You get this little wiggle here. So you see that second order underdamped response along with that more dominant long-term decay, first order decay. Yeah. So since I said step, we should probably stick to step, but you could easily do the impulse response as well. So obviously this is very useful, very powerful to use Matlab to explore a transfer function for us. So we can look at the pole zero map, we can look at the poles, we can do some simulation with the TF models. We could use the symbolic toolbox to come up with nice symbolic expressions of the transfer function. Yeah. And we learned how to sort of manipulate them. You can multiply them together, and you can create them in different ways. You can create them from state space model or directly, and yeah, do some simulation with them. So really powerful tools. There are similar tools in Python too. Python has a control systems toolbox that can do a lot of these things. There's some functionality, especially when you're converting from one form to another, that isn't there in the Python version, but I expect in the next couple of years it'll be even better. So yeah, I like using it. I use it. I try to contribute to it. So yeah. Any other questions?